Welcome back. So we are honored to introduce our next distinguished speaker, Professor Remi Abgrall from University of Zurich. He's renowned for his significant contributions in computational fluid dynamics, the numerical analysis of conservation laws, the multi-phase flow, and Hamilton-Jacobi equations. Additionally, he also holds the title of SAM Fellow, and let's welcome him as he takes the stage.
So thank you very much for this nice introduction, and also thanks for the invitation. So I will talk about a classical topic, so conservation problem of hyperbolic problem. So what can we do around this? What is the problem? So this is a joint work with many people. So Mario Ricciuto in France, Svetlana Tokareва, she was a postdoc with me, Paola Bacigalupi, PhD, Ksenia Ivanova, postdoc, Philippe Höfner, also postdoc, etc., etc. And if I have time, I will talk about the last part. So it's done mostly with Vassily Barzukov and Yong Ledu and Jean Fangli from who are postdocs in Zurich. So, well, so what is the problem? So, well, I will start very basics with basic things. So if you have a hyperbolic problem, so what like this, so think about Euler equation, but not only. So what you do, because you work in the domain omega, so you need to discretize this omega by some meshing tool. Then you need to approximate the solution space by the H. Then you need to do something with divergence of the flux. And finally, if you like the method of line, you will do something with time. So in practice, omega will be approximated by polygonal shapes, mostly simplex because of mesh generators. So most methods use for this problem functional space where discontinuities across the boundary of the element are automatically embedded. And one of the motivation is that there is a common belief saying that this will able to allow to enforce local conservation. It's not completely true. Then you will choose a variational formulation of the divergence term. As I said many times, the method of line. And in my talk, I will explain, in fact, that global continuity can be used. Well, it's not a new fact, but you can show, in fact, that even finite element approximation with continuous elements, stabilized, of course, can be seen as a finite volume scheme. And so local conservation is automatically enforced. So this is my talk. So the classical setting is about, so I recall a crash course for master's students. So you have this problem, and mostly my problem will be the Euler equation, where the variable of the constant variable is mass, momentum, total energy. The total energy is the sum of the internal energy and the kinetic energy. So V is the velocity, ρ is the density, and the internal energy is mostly obtained by, it depends if you have a complete equation of state or not. But if you have a complete equation of states, you need an additional variable, which is the entropy, which satisfies the Gibbs identity in the simplest case. And this depends on P, so this parameter, the pressure and the internal energy, and by thermodynamic relation, like here, you can recover everything. So from the Gibbs identity and this relation, you obtain that the entropy, the specific entropy follows the transport equation. And if you are a mathematician, you will introduce a mathematical entropy minus rho s, which satisfy for smooth solution an additional conservation law. And this function is a convex function of the conserved variable. And to get this, what is really done is you start from the Gibbs identity. You write internal energy in terms of the total energy. So implicitly, you introduce what is called the entropy variables. And then you dot multiply this relation by the entropy variable. And you see that if G, the entropy flux, so here V VS satisfies something of this type, then automatically you will have a conservation relation on the entropy. And in fact, this is meaningless. You know, one of the reasons is that you have, say, 3 unknown and 4 equations, so something is redundant. And from thermodynamics consideration, we know that the good relation here is not an equality, but an inequality. And in depth, you use the fact that the entropy is convex. So it's very well known that this kind of problem generates discontinuity. So the simplest example is the Burger equation, which can be seen as a very, very special case of the Euler equation. If you take the specific heat, so the pressure is equal to the gamma, the specific heat, minus 1 times the internal energy. If you choose gamma equals 3, and then write the characteristic variable of the Euler equation, it turns out they are a straight line, and moreover, they satisfy a Burger equation of this type. So here, u is no longer the velocity, but one of the 2 Riemann invariants. And if you integrate this like this, by using the method of characteristic, you receive, this is also, of course, very well known, that starting from this initial condition, after a finite time, the gradients become steeper and steeper, and then you have a creation of shock. So this writing first is meaningless. And second, you have to do something with this. So this is very well known. So this is comes back to Peter Lax, but I'm sure it was done by people in mechanics way before. This is simply a principle of conservation, but he formalized it. So you take this, you multiply by a compactly support test function, apply the divergence theorem, and you end up with this relation. So and the beauty is that you no longer have derivative on the conservation variable and the flux, but only on the test function. So any solution which satisfies this for any test function will be called a weak solution, and you can do the same for the entropy relation or inequality, provided that you take positive test functions. And the combination of the two will be called, if this exists, an entropy weak solution. And of course, there are all the classical problems of existence uniqueness. It's very well known for scalar problems. For system in 1D, it's well known, but in multi-D, immediately it becomes terra incognita. So now I'm interested in, not really in the math, but in the numerical approximation. So how do you compute this guy? So you have 2 versions of the same problem. So this is again a Burger equation. Before I had the non-conservative version, du dt plus u dot du dx equals 0. And then you can write equivalently for smooth solution into this conservation form. And so you have 2 interpretations. You take R, you chop it into cells, so A, B. And then either you look at this formulation or that formulation. And then in the first case, I take the non-conservative form. To simplify, I will assume that u is strictly positive. It's not essential, but it simplifies the discussion. So here you will interpret u as approximation of the solution at point value and at time steps, Tn equal n delta t. And because u is positive, then you know that the characteristics are on your back. And so I will not say good approximation, but a legal approximation of the PDE would be this one, because you can easily show that it is stable in L infinity. Assuming that u0 is positive, then you can show that un is always positive, and then you automatically have a CFL condition which ensures the stability in L infinity. But now, if you take the same mesh but introduce midpoints, so you introduce control volumes, you integrate your PDE on the control volume. So now you're going to interpret your data as the average value of your solution at time Tn and inside the control volume. And then formally, you take this, you integrate in a control volume, and you end up with this. So you have to define numerical flux, so f hat I plus 1/2. And because here I have assumed that u is strictly positive, so a good one is simply the upwind numerical flux. And again, you can show that under a CFL type condition, then things are stable in L infinity. So what is the difference between the two? For this, you implement this on a computer. You take many points, and you look to where it converges, if it converges. It turns out it converges. We also know how to compute the exact solution. So the exact solution is in plain line. And in dotted, with crosses and dotted line, you have the solution of the non-conservative formulation. And with circles, you have the solution of the conservative system. So clearly, the non-conservative system doesn't provide the right answer, but the conservative formulation does, at least for this case. And the reason is very well known. So it's explained by the Lax and Wendroff theorem, which was written in 1960. And it says that if your scheme has this formulation, so you update the solution by the balance of the flux at the boundary of control volume, you have an initialization which is of this type, but this is not essential. This numerical flux is a function of your arguments. You assume that it's consistent, meaning that if all the arguments are equal, then you recover the exact flux. This function is continuous, or Lipschitz continuous. And if the scheme is stable in L infinity, and if there is a subsequence which converts into some LP to some function V, then this V will be a weak solution of the problem. And the proof is very simple. You simply multiply by approximation of the test function. You make a discrete integration by parts. In French, it's called the Abel summation procedure. And then you end up by using the Lebert convergence theorem. This can be extended in multi-D. So everything is nice. So it should be the end of the story. But I don't think so, fortunately. So there are many questions, in fact. The first question is, so I had a non-conservative formulation of the Berger equation. So what does it converge to? So there is a partial answer by a paper by Tom Howe and Philippe Lefloc in Math of Comp in '94, so it's difficult to read. And what they show is that under the L infinity, under L infinity stability condition, plus a subsequence which converges strongly in L1 log to, then this subsequence will not converge to a weak solution of the initial problem, but a solution of the same PDE where the zero is replaced by a Borel measure. And what they conjecture in this paper is that the Borel measure is sitting on the shock waves, or the discontinuity, sorry, of the problem. So here, typically. And they conjecture it's a form of a sum of Dirac multiplied by some parameter, which depend from the left and right information of these discontinuities. And so you have as many terms as discontinuities. But they don't provide any information on the strength of the Dirac. And in particular, it can be zero. So if it would be zero, then you would have the right solution. And so the first question is, can we play with this? So it seems to be just a stupid question, but I don't think it is so, because, for example, if you take this Berger equation and you make this change of variable, so it's very well known, and you teach this in any master class, that you should never do this simply because these two PDEs are equivalent if the solution is smooth. But as soon as there is a discontinuity, they don't provide the same weak solution. And the answer is that the shock, which is given by the Rankine-Hugoniot relation, will have different speeds. So you should never do this. But you really want to do this because there are problems like in fluids, where if you're a mathematician, you play with this form. But if you are an engineer, you would like to play directly with the data of interest, which are certainly not the total energy, but the pressure, the internal energy. So you want to play with the pressure. But if you play with the pressure, you lose the conservation. And so this is why most, if not all the codes, use this and not that. But, and there are other questions. For example, if you do MHD, so in the you have to add the Faraday law here, plus the divergence B equals 0. But in the writing of the total energy, you have to introduce a magnetic energy. And if the magnetic energy is very, very strong, if you make a mistake in the evaluation of the total energy, then very likely you will have negative internal energy and the code blows up. So you really want to do this, but it's forbidden by the law. So because I'm French, if there is a law, there is a way to overcome the law. So I will try to explain how you can overcome the law. And there are other things. For example, there are many codes or schemes in the literature and also in industry. For example, one which is coming from idea of Tom Hughes and Klaus Johnson a long time ago. So it's a SUPG. So what they do is they multiply, this is for steady problem here. They consider the hyperbolic problem, multiply by test function, integrate. So it's going to be unstable. So they add a particular stabilization, which is here. It's a weak formulation of a Laplacian, but not a Laplacian, a classical Laplacian isotropic, but a streamline Laplacian. So it's a Laplacian which lives on the streamline of the solution. And for dimensional purposes, you need to introduce a matrix here, which has a dimension of the inverse of a speed to compensate this guy. And then for dimensional purpose, you need to introduce H. So this doesn't look like a finite volume scheme, but this works very well. And it has been even used in industry by a French company, for example, Dassault. And it works. So there are variants of this by using the ideas from Eric Burman and Peter Hansbo, using jump stabilization. So if you look at DG, okay, the average is evolved like a finite volume scheme because it's designed in such. But there are other information. So what is the connection between all of this? There are other schemes, for example, by Kuzmin using FCT technique, and you don't see the flux, or Jean-Luc Guermont also. And I worked a lot of long time about on this scheme, which are called residual distribution schemes. So it comes from Filro, and again, you don't see the flux, but they work, and you can prove they work on paper also. So what is the connection? So my belief, my opinion, is that you have to slightly modify your point of view about conservation. So what you do when you discretize this thing, but first, as I said, you need to discretize your domain. So here, for example, you will take simplex like this, triangles, quads, or in 2D, but in 3D, tets and eggs. And then you introduce the freedom. So here it will be my point values. So I'm seeking P2 here and Q2. I call sigma my degrees of freedom. And so in each element, I have a polynomial. And I will also enforce a global continuity. Well, it's not essential, but just to show that I can go to this extreme. So phi sub sigma will be my Lagrange interpolation polynomials in each element. So this discretizes the space, and then I need to discretize the divergence of the flux. And for this, I introduce, I will show example, what I call residual. And the only constraint I ask to these functions, which depend on u sub h, so the index are sigma for the degrees of freedom and k for the elements. So the only condition I impose for now is that for any of each element, when you add up this quantity for all the degrees of freedom in the element, then you will have a discrete approximation of the normal flux. So here by this symbol, I say there is a quadrature formula. And the only thing I ask to the quadrature formula is that if, so it's carried, for example, on this edge or face, then it will be the same quadrature formula since from the left and the right, of course. And then you integrate in time by some technique which are a bit more complicated than this, but it's not the point here. And so what you can show is that you have a Lax and Wendroff theorem, and basically, if these radial are, say, Lipschitz continuous of their arguments. So they have a finite number of arguments, which is related to the fact that the mesh is regular in the finite element sense. You have this local conservation property. So this has been first seen by Phil Rowe long time ago. And if you have a subsequence which converges to something in L2, and if this is bounded in L-infinity, then this U will be a weak solution of the problem. And you can do exactly the same for entropy. Bon, so one day I went to Onera, so the French NASA, and I explained that my stuff is absolutely fantastic to one engineer. His name is Bernard Courbet. And he said, oh, very nice, but I don't believe you because I want to see what is coming in and what is coming out. Where are the flux? Okay. So it took me 10 years to find the flux. But to show you this, let me explain that you know very well this technique. So if you do 1D, this will be your finite volume scheme. And I write it like this. So I take, so for finite volume, you have this control volume. I will approximate the solution on the point values here. And so here I update by taking this flux minus that flux. And what I'm saying is that it's a sum of a contribution which lives on this part of the interval xi plus 1 plus a contribution on that part of the interval xi minus 1. So this explains that this interval will send information to the left, and that interval will send information to the right, and you gather them together. And you can rewrite the finite volume scheme by simply adding and subtracting the value of the flux at the midpoint, and this will be my residual. And of course, when I consider this interval, I add these two quantities. So I've just shifted the index by 1. And you see that this plus this, the numerical flux cancel, and you get my conservation relation. So any finite volume scheme is of this form. So in fact, but if you take SUPG now, so I need to write the residual on each element. So I use every time that the sum of the basis function will be 1. And so this will be my residual. So the only things which seems to be not very natural is that you will have a boundary term here, but you need it to get my conservation relation. The boundary term will cancel when you add up the residual. And then you recognize the weak formulation of SUPG. So for Galerkin stabilization with jumps, it's exactly the same. Instead of this term, I had this kind of term. For DG, you would have a residual, which is what you would consider. For all the scheme I know, except one that I might sketch at the end, I can write this. So now, let me show you that any of these schemes, so continuous finite element, has a finite volume formulation. So this closes completely the question of the local conservation of continuous finite elements. So this has been studied by Tom Hughes, and there are another paper by Quarteroni, etc. But to my knowledge and to my readings, there is no explicit formula of the flux. They show that it exists, but what I want is to have a formula. Alors, first, I reproof again that the finite volume scheme is a residual distribution scheme. So here I will take this funny control volume. I could take a triangle, but I have decided to do this. So my degrees of freedom will be on the vertices. So it will be second order implicit in my mind. And then I update the value here by taking the numerical flux on the boundary. And you can see, so it will be the sum over the flux on the boundary. So you can rewrite this as a sum over the triangles of the flux here and there. And then by adding this quantity, dotted against the normal here. So the sum of the two normal is this normal, which is 1/2 of this. They sum up to 0 because the boundary of this polygon is closed. So, and taking this, so this So I have ordered the flux in a clockwise sense in my internal element. This is why there is a minus here. So this, when I add this, I have exactly my finite volume scheme. It's just a rewriting. So I can, you see that a finite volume scheme is a resonance scheme simply because when I add, considering one element, I consider these three quantities. Of course, the internal flux will cancel, and I will have the sum over the boundary of this quantity that I can interpret as the integral over the boundary of the P1 approximation of the flux. So P2, for P2, I could do the same. And P2, in fact, is more inspiring because it's more complicated. So I will define a multidimensional flux as a function of many arguments. The only thing I ask is that when they are all equal, so the index is n, there is a normal that I have to find. When they are all equal, I simply ask that you have this consistency relation here. And what I want to find, so having my 6 degrees of freedom here, I want to write this 6 degrees of freedom as a sum over the edge of this triangulation in dotted line of flux to be computed, plus, inspired by what I said in the P1 case, a contribution on the boundary. So by conservation, if I flip 2 degrees of freedom, I should put a minus. And this F boundary is how I interpret my contribution on the boundary. And then there is some form of, it's a bit arbitrary. For example, for SUPG, I have decided to put the integral over the boundary of the test function that multiplied by the normal flux. But I could have added something else. The only condition is that it cancels. So I have this freedom. So how I interpret my contribution here? So looking at this relation, because I'm supposed to know this and that, I introduce psi. And then by using the fact that when I flip 2 degrees of freedom, I introduce a plus and or minus 1. What I'm writing is that I have a linear combination, A against the vector of the flux, equal psi. And this A is the incident matrix of the graph here. So I choose an order. So I choose an orientation of my graph. I have one incident matrix, and I write this. And by simple argument of graph theory, you can show that there is a unique solution of the problem, which is written like this. So you have an explicit formula, because the kernel of L, so we know that there is only one eigenvalue of L, which is 0. So the kernel of L is one-dimensional, and it's carried by 1, 1, 1, 1, 1. And this kernel is exactly the kernel which expresses my conservation relation. So thanks to this, I can write this here. And for example, for P1, if I take, say, finite element formulation, I have my phi. I take an interpretation of phi. Then this will be my flux, and this will be my normal that I obtain by consistency. If I do P2, boy, it's a bit more complicated, but it's like this. You have explicit formulation. And for the normal, you simply replace the psi by the normal. If I do DG, I can also write a flux. If I do DG3, so I have my graph here, I write my relation, and I get the Laplacian inverse, and then I obtain explicitly this. So, in summary, for this part, all the schemes admit finite volume formulation, except one, I will show. And this is a consequence of a different way of looking at the conservation of the... You don't look at the conservation at the level of faces or edges, but at the level of elements. So this answers the question of my guy, Bernard Courbet, except that I was 15 years late. I didn't get the contract. And is it only for fun? Alors, not only. Alors, why? Because you can, so this is joint work with François Villard, a former PhD of mine. He's now in Montpellier. So he likes DG. Well, why not? And so he, he has a DG code. Well, this is a typical SL. It can be a triangle or a polygon. So what is easy, so this is published in this paper, is to see that there is a one-to-one mapping between polynomial representation and piecewise constant approximation on cells. So here we take these 10 cells, so it means that here we have P3. And there is a one-to-one correspondence. So we can equivalently represent a polynomial by its coefficient, moments, what you prefer, or by the constant values. And then we have an equivalent way of rewriting the DG code into some form of a residual distribution scheme. And then we have used this to do the following. So we have this is a KPP problem, so you have a shock, it's a non-convex problem, and it's a bit complicated to compute. So he started, he did the calculation by a non-stabilized DG scheme. So you will have oscillation at shocks. So there is a way to detect these oscillations. And so when you flag a cell, you have a way to flag which subcell which is not good. And so assume this is S9. So using what I said before, I have ways to compute flux across these edges for all this. I can rewrite the DG scheme as a finite volume scheme where I have an analytical expression of the flux. Now this cell is not good, so we replace by say first order scheme, say like local Lax-Friedrichs. We replace the scheme with the flux we had computed before by the local Lax-Friedrich scheme, and then we go back. And thanks to this technique, so it's we can monitor the L-infinity bound on the solution, at least in practice. So this can be extended to Euler, etc., etc. Voilà. Another application is, so this closer part of the flux, is that as I said before, for example, you take Euler, you have the Euler equation plus the entropy inequality. And it's very important to have schemes which satisfy entropy and entropy inequality. If you have many entropy, as many entropy as you wish, and maybe other constraints, at least algebraic constraints. For differential constraint, I don't know how to do. So let me take the example of the entropy. So what is the problem? So I take my scheme, so which is described my residual. I have this conservation property. And then I have my entropy equality or inequality. So I want to construct from my scheme, a scheme which is entropy stable or entropy dissipative, and I want to control exactly the amount of entropy I'm adding. So how do you go from here to here? You simply dot multiply by the entropy variable, so the gradient of the entropy. And this relation is nothing more than this. So if you do this at the discrete level, you would like to dot multiply your residual by the entropy variable. And you would like to have this, if you want to have conservation, you would like to have this property. And this is of course not true in general. There is no reason that starting from this, dot multiplying by entropy variable, you will have another fantastic equality of this type with precisely the entropy flux, which is obtained here. There is no chance in general that it works. But nevertheless, how can you do it? So the trick is to perturb the initial scheme by adding a perturbation, R, which is indexed by the element and the degrees of freedom. And you want to construct this perturbation by following, so first you need to have conservation, and you want to have conservation of entropy. So conservation, it means that the sum of the perturbation will be 0. And the second relation, by just doing the calculation, it means that you want that the perturbation satisfies this relation. Here, you know the G, so you know this because you know UH, and you know this. So this you know. The only thing you don't know is R. Alors, there is a trick. It's there are many ways to enforce this. Is to define R as being alpha, a parameter, multiplied by V. So V is the entropy variable, minus the arithmetic average. So why? Because if you do this, automatically whatever alpha, the sum of this R will be 0. So automatically you will have entropy conservation. And now you plug this relation into that formula, and you get this relation. So you have a unique alpha, at least if V is not locally constant. Locally means in the element. And what I have done is simply adding to the if you can see the scheme as being the PDE plus some second order term, and you add not a dissipation, but a second order term where the divergence of K nabla V, where K has a proper sign. So if the scheme is initially entropy diminishing, you will remove entropy because I want to keep conserve entropy. And if you don't dissipate enough, you will dissipate more. And if, of course, if you want to have an entropy inequality, you will not remove entropy if you already dissipate entropy. But this is the extreme case. And the second thing is that in the formulation here, you have the choice of how you interpret this term. In fact, G. So there is a flexibility again. And we can choose, I have a way to do it without losing any accuracy. So this extent this was done for DG, for this particular setting, but this can be extended to DG. This is well known. For example, there is a paper by Shi Wang and many others where they already have done that for DG. There is a full technology by people in Canada, for example, or people at NASA. The main difference here is that, well, first, we always keep the optimal order. We don't need to have special quadrature points. So here the complication is, for example, in this paper by Zink, he works with triangle, is that you have to have the quadrature points inside your elements talk well to the boundary point. And this is a very difficult question. And so here we don't need to, it's only the boundary talks to the boundary and no more. And in fact, in this paper, we have played with this to show that you can stabilize a nonlinear, linearly unstable scheme. So for finite element, we take the finite element formulation without dissipation, so it's unstable in general. And we can stabilize this simply by this technique. Of course, there is no mistake is allowed either. If you make the slightest mistake in the code, which means that there is a bug somewhere, boom. So it's a way to debug also, but cheap. So it works, for example, for Burger. It's not Burger because I have taken this flux, which is convex. And why is this flux? Because I wanted to make sure that none of the quadrature formula I know will be exact for this. So this is my mesh. First, well, I don't know if you see anything, but so with this boundary condition here, you will have a shock and a fan. So I think I have a plot later, but you can see that if you started from second order, you get second order in the fan. Of course, in the shock, it's a different story. If you were third order, you stay third order. Oh, voilà. So one of the reasons is that I did this is that in the very, very old version of this RD scheme, they were very good on shocks, but not very good on fan. For example, you see there are wiggles, which are not instability, it's simply that we have spurious modes. So I have the technique to modify this, but I needed to depend on a parameter, and here, well, it's very insensitive to the parameter. Of course, there is a price to pay. You completely kill the shock, because I want to be entropy stable. If I want to be entropy dissipative, then I can keep this. So we did this for Galerkin, pure Galerkin method with CIP. With this correction, so it's we manage without stabilization to run the code a bit longer. This is a 2D version of Schuh-Osher test case. Again, it works very well. And so in this paper, we did this on the entropy, but in fact, if you have several constraints, like you want to constrain the kinetic energy or things like that, we have a way to do this using the same technique. So the plus of the method, if there is any plus, is that it's completely automatic, and really the quadrature formula that you are using to compute the surface integral do not play any role. It's only what you do on the boundary which matters. So it's very flexible. So again, another application of this view, a way of seeing at local conservation from the element point of view is the following. So in this paper here, there is they like to. So this is coming from the Russian school. They like to have in the PDE the mass, the momentum, but no energy, the entropy. Because there is a belief, and I believe this is true, that the better parameter is to control the entropy. But then you lose the energy conservation. So by using similar techniques, very similar technique, and this is described in this paper, we managed to construct a scheme using the entropy and not the energy, but which is discretely compatible with a conservative discretization of the total energy, which means that you are going to converge to the right solution. What else? Another application is that now if you are a fan of staggered mesh, so you localize your, again, you start from this formulation of the PDE, so you have mass, velocity, and internal energy. So you are going to store the thermodynamics in the elements, typically by polynomials, piecewise constant or linear, quadratic, etc. So it will be the density and the internal energy. And the velocity, you will store it at the vertices. You will have a globally continuous approximation, so P1, P2, etc. And so how can you design a scheme which will be guaranteed, provided that everything is stable, guaranteed to converge to the right solution here? Because here, everything is in conservative form. So the trick, first I show it works, so in 1D, so this is SOD, so you recover exactly what you want. In multi-D also you can compare as well. And I will have no time and I don't want to bother you too much. But the trick is the following. So you, I have this. So what is important is to keep mass. You must conserve mass. And this is very well known for people in doing Lagrangian hydrodynamic. Mass is really the things you should never drop. So you keep this. So here you will do, for example, DG. Then here I will first construct a linearly stable method for this. So what I do, I multiply by test function, and I cannot integrate by parts. So I apply quadrature formula, and I do essentially what I can. And I know it's not going to work. The only thing I want is that it's stable. And here again, I will do multiply by test function. So my test function here and there will be discontinuous across elements. Here they will be globally continuous. So I will use my RD technique before. And again, I apply a quadrature formula. I cannot integrate by parts. I do what I can. Then, now I look at what I would like to have as a weak formulation. So for mass, it's built in. So now I do it for the velocity. So I can write, because it's essentially a finite element formulation, my update as a sum over elements of things. I will call residual, except that they don't satisfy a conservation relation. And so I will perturb the residual, and I will perturb it in such a way that I'm going to get conservative. Alors, how? Because how would I do at the continuous level? What I would do, I would multiply this by u and add the two equations. So I will multiply by u my relation on the mass, using the fact it's by dg, so it's each element is independent. I will add it to this. Again, it will not work. So I need to perturb the residual here, and I will construct my perturbation in such a way that I have a discrete time and space residual. And how do I take the time and space thing? It's simply because I have to update rho time u, and we know that rho time u at time tn plus 1 minus rho time u at time tn is rho time u is rho n plus 1 minus rho n multiplied by some average of u plus the same here. So I choose the average. By average, I mean the average between un and un plus 1 in such a way that I'm using only data that I know. What do I know? I know rho n plus 1, and un. So I will write my update of rho u using only rho n plus 1, and un. This is obviously doable. I end up with a linear relation, and I can explicitly compute my perturbation. And then once I have done this, I will do exactly the same for the total energy. And so, in a nutshell, the only tools you need to use is something like a square minus b square is a plus b times a minus b. This is the only thing you need to know. Plus this idea of having conservation by elements. So this is explained in this paper, so I will not go into the details. And I think my time is over, and I will skip the rest, which is the only example I know of a scheme which also works. You can prove it works, but which cannot certainly not be written in flux form. But another time, maybe.
Okay, so is there any questions? If there's no question, maybe let us thank our speaker again, and maybe we can discuss with the speaker personally afterwards. Okay, thank you.
Thank you.